So what we'll do is we'll spend about a minute and a half on the first question, and then I'll start asking for who's brave and wants to go up and work this out.
I'll do it.
Okay? So take a look at the first question. Take a look at the first question. Put your calculators away. All right, stop. That's about a minute and a half. I didn't start it exactly on that. But let me ask, just with a show of hands, how many actually were trying to calculate this out?
First time.
Okay. This is actually requires absolutely no calculations. Okay. Let's look at the problem. Okay. It says that the abundance of lithium-6, which has a molar mass of 6 point whatever AMUs, is 7.5%. Is that a high percentage or a low percentage?
Low.
That's a low percentage. So very little of all the isotopes on the periodic table is this isotope. It says the abundance of lithium-7, which has that molar mass, is around 93%. So this thing is what? Top heavy or bottom heavy? And when I mean top heavy, does it weigh a lot or does it weigh a little? Weighs a lot. In other words, lithium, this is mostly made up of lithium-7, right? So which can I cross off right off the bat? A and B, very good. So I can eliminate A and B right off the bat. Because if I look at this mass here, 6.0, let's say 0.2 here, and this is 7.01, there's no way that we can have a percentage that's so high that we're going to have these values. They're just too darn close to that. All right. If I look at D, what's wrong with D?
Too high.
It's too high. It's above this number right here. By doing that, you already got your answer. Yes, Sam?
Wait, could you have looked at your periodic table?
Yeah, you'll have the periodic table at your access.
Well, I mean to solve that.
What does the periodic table say? 6.94? That would have been a heck of a problem-solving technique.
So I just, yeah.
You got to get out your periodic table then.
Hey, look at that.
Problem solving.
But like
Problem solving.
If this showed up on another,
Next.
would it still be the right answer if you looked at a periodic table?
You will always have the periodic table and the equations in front of you.
But like, the periodic table, if I used it, the periodic table for that problem, it'll always be the same.
It would have to be, unless they said like element X. So some mystery. So see the problem solving skills? You have to be able to use what's available to you. And I didn't tell anybody to take out the periodic table.
I did.
Sam did.
No, I
Sam, how long does it take you to answer it?
Oh, actually, I didn't get it, but right when you said how many of you use math, then I was like, then it clicked. So I spent the whole time trying to work it out. But
I told you this stuff.
Now, if you were to work this out, and if you had a calculator that you would use, because I want you to know this process, because you can use some quick mental math. But what is the process if I wanted to actually calculate with your calculator? Anybody remember that? What is it?
Like multiply the AMU by the decimal
It's
point.
like 0.015121 times, what'd you say?
0.075.
Yeah, 0.075. You get an answer there. Do the same thing with the other one.
Does it track?
No, hang on. Let's get this first. So point what?
0.925.
925. You get a number there and a number there. What would you do? Add them up. So it's the average of all the isotopes. Now, it's kind of like if you're taking a test. You're calculating your grade in a class. If you're in a class where every point is equal, that's easy to find out what your average is. But if you have, say, your test points, like in here, what is it, 60%? That's the weight, and then your labs are 25%. So then you have to do some funky things, all right? But if everybody's the same, then you simply, or has the same weight, then you just simply take that plus that and divide it by what? 2. But since they're not the same, we have to multiply this by the percentage, this by the percentage, and add them up. Because technically that's what we're doing when we take a number and multiply it by 50% and another number and multiply that by 50%. You're really taking those two numbers and adding them up, okay? So that's the type of mental math that we're going to have, and you're going to see some isotope type questions on the test on Wednesday. Okay. So with that in mind, try the next one. And time. All right. Now, whenever you're looking at these problems, you should always ask yourself, is there at least one or more that I can eliminate?
Yes.
Okay. You say yes? Why?
Because, I mean, one of them is like too small. I was just close to, as close to one of the masses.
Go on.
So I eliminated B.
You eliminated B. Did anybody else eliminate B? Or did anybody eliminate anything? Or you just, good Taylor. So you just kept them all in there? That's one of the things, when you first read the question, there are going to be, or hopefully there'll be, like a what? Why is that in there? B is one that you can definitely eliminate. So when you get to the point where you're like, ugh, I have to guess, you're not going to accidentally pick the dumb choice. Okay? So looking at this, now we're looking at three answers that are, quote unquote, relatively close. Right? I mean, 64.7, 65, and 65.3. I'm going to tell you on the actual AP exam where you're actually taking it, they're going to be a little bit farther apart. Did anybody get a value for this one? Or an answer? Yeah, Rishi?
65.02.
65.02. And how'd you get, wait a minute. Oh, is your actual answer?
Yeah.
Okay. So what would be the best choice or best option on here? D as in dog? Did anybody else choose D? Okay. Rishi, come up here and show me what you did. Talk it out. Hey guys, I'm not going to be the only teacher in here. You guys are going to help teach everybody else. Didn't use a calculator, right?
No.
Good man. Checking over there. So talk out your process here.
Okay, so it says there are two isotopes. So the first isotope, it says it's a mass of 64.23 AMU, and it has a 26% weighting.
Right.
So 64.23 AMU and 26%. So I just automatically converted it to a decimal.
And as you're doing the multiple choice question, I'm going to interrupt you for a second. Don't worry about units. Just, you're trying to get numbers through, okay? So you did that calculation, you came up with a value, and...
Yeah, so I'm just going to write down the calculation. 16.6998. I don't want to go through the whole thing.
Perfect.
So I got that. And then the second, it says there's a mass of 65.32, so 65.32 AMU, and it has, so 100 minus 26, it would be 74% weighting, so
Good.
0.74.
And don't freak out that that wasn't given to you. I know some of you are like, that doesn't bother me. But I guarantee you it bothered at least 2 or 3 of you in here. I'm not going to ask who, but I know it did. And so you did that calculation, and you got what?
And then I got 48.3368. And then I just I didn't want to add all those digits up, so I just kind of rounded 48.33 and then 16.7. And then that would be 65.03,
Good.
but that would be match. It would round
That'd
up
be
to
the closest or the
yeah.
best option. Good. So in this case, a minute and a half, and again, you're wondering, is that enough time to do all that? I think so. It might take some of you 2 minutes, but again, it's something that is well within the easy realm. Yeah, Timmy.
So instead can I do 64 times 0.26 instead of decimals?
Absolutely, yeah. But be careful with that. I mean, if the numbers are this close together, you might want to go one more decimal place. But did you do that? Did you do 64 times, what was that, 65?
That's 64 times 0.26.
And what'd you get? Oh, okay. So it was taking you time.
Yeah.
Okay. So find that quick method. Okay, good. All right, try this next one. All right, that's a minute and a half. All right, this is a rather wordy question. Yeah? And last year the AP exam changed in that the questions got more wordy, there were more pictures, and so it's causing you to have to look at the problem in a little different way. It's not just, I've got a short sentence and I want an answer. So whenever you see a lot of information, probably the first thing you want to ask yourself, what is the question? What is the question this one is asking?
Underline what's the point.
What's that?
Underline what it is.
Yeah, I know, but what is the question?
What is percent?
What is the percent? Good. So we're looking for the percent and, more importantly, the heavier one. Okay, so we're looking for the percent of the 86.9. Okay. Now this is a pretty big range. We've got, we're going to say that that's 85 and that's 87. Does that seem fair? We'll say that's 85% or 85 AMUs, and we'll say that's 87. That just helps to clear the water up a little bit. All right. So if we look at the periodic table, what is, number one, what is rubidium?
RB.
RB, okay. And what is the molar mass?
85.47.
85.47. So there's another piece of information that we need to have, and that's in grams per mole, but not necessarily needed for this problem to have the unit on there. So when we look at that and we say, okay, we've got one isotope, this is comprised of two different isotopes for considering the molar mass. We have one isotope that's 85, really close to the 85.47, and then we have another one that's 87, kind of far away. So which option or options can we get rid of? I hear A and B and I hear C and D. Kendall, what did you eliminate? Did you eliminate any of them?
No.
No? Taylor, did you eliminate any?
C and D.
Why?
Because it's asking the percent of the heavier.
Okay. So right off the bat, we can get rid of two of these. Okay. Because we're looking at this and we're saying, well, the actual mass or molar mass for rubidium is a lot closer to the 85 than the 87. If I had a high percentage of the 87, what's going to happen to my molar mass? It should be higher. It should be closer to the 87 since we only have two isotopes. Okay, so we can eliminate those two. Then, from here, we'll look at it a little more closely. Okay, so one thing that we want to do or start doing is actually identifying what the question's asking, right? So this is a question, but even more so, say, hey, it's wanting the big guy, the heavier one, okay? Let's see here. Timmy, what'd you do?
Well, I just guessed. I had B.
You had B. Anybody else pick B?
Got finished.
And that's a pretty good answer.
Can I?
Okay? Because the reason why, without doing any calculations, and this would be one that I would read through, kind of stop, process for a little bit, and then say, you know what? If I look at 13%, if it's going to be 13%, I'm willing to bet that that mass, or this mass, I'm sorry, the molar mass would be a little lower than the 0.5. This is essentially 85.5. So 28, without doing any calculations, seems good. But the key here is elimination, okay? And reading the question carefully. So mark up your test. Simplify certain things. Identify what the question is really looking for. Eliminate things that have no business of being there, number one. Timmy, is that a question?
Yeah. Why did we eliminate C and D?
We eliminated C and D because if the percent of this isotope, 87, was in the 72 to 85 percentile, I guarantee it'd be over 86. It'd probably be at 86.5-ish if I were doing my mental math right. So when we look at, okay, and again, it goes back to this process here. So when you look at your molar mass and you do your percentages, what should you be getting? Okay. Okay. All right. Just to speed things up, which one can we eliminate, or which ones can we eliminate?
A and B.
Good, Lucas. Okay. Again, nitrogen's 14, oxygen's 16. Be thinking, okay? If we're looking for a 36.8%, and this is kind of a dirty question in my book, because it does guzzle up time. But like when you're taking standardized tests, and you have an opportunity to eliminate possible answers, and you get down to the bell, then it makes it a little easier. Your guessing is a little more intelligent. You're not picking the wrong answers right off the bat. All right, that's the minute and a half. Okay? All right, what I did when I was working this out without a calculator, I just started with this one and found out what the percent was. So I have 14 grams, and I'm not doing 14.01. Okay, I'm not including those that are close. I'm going to round these to speed things up. So I have 14 plus 2 times 16, which is nice, is 32, and that equals, what is that, 46?
Yes.
So the total mass, molar mass of that is 46. So if I do 14 divided by that, and multiply that by 100, what percent do I get? Anybody do that one?
Guessing.
30, very good. And you would need some time to do that, okay? But that's what your strategy is. You're taking the mass of all the nitrogen, dividing it by the total. So C's out, okay? So I would go right to the next one. Why would I not go to E?
Too big.
There's a lot of oxygen there. A lot of oxygen. If I look at that, that's a 28, and 5 times 16, what is that, 80? Yeah, so roughly that's 100, and I know that there's no way that that's going to be close to 36, and I think that's closer to the 28, 26, 27%. So I can now eliminate that. If I have time, after I've answered all the other questions, this would be one that I'd definitely come back and double check, okay? I wouldn't mark it on my key just yet, but make sure that you come back and do that math real quick, and you'll find out that it's really close to 36%. Okay?
So that's D, right?
D is the correct answer.
Okay.
All right, let's look at number 37. All right, number 37. Question asks, how many moles of O2 are required to oxidize 1 mole of CH3CH2COOH according to the reaction represented above? Okay, so the question wants to know how many moles of oxygen. Now, there's also an extra caveat here. To oxidize 1 mole of this. So we have to keep that in the back of our mind. So if we have a value here that's not 1, then we get to do something. And probably do get to do something since the question was asking that. I'll admit in class, I didn't read that component, and the incorrect answers were listed here, so we can do it correctly now. All right, so again, inventory if you need to. So carbon, we have 1, 2, 3 on the left side. Actually, I'm just gonna move that down. I'm gonna put hydrogen first. Hydrogen, we have 3, 5, 6. Carbon, we have 3. Oxygen, looks like that's the only one left. So we have 2, 4. So it looks like we need an even number of oxygen on both sides. So again, I'll put my hydrogen first. I have 2. Carbon, I have 1. Oxygen, I have 3. Excuse me. Okay. So again, it's a good idea. Start with the hydrogen, balance out the hydrogens to make sure everything's okay. And as I said earlier, make sure that you keep this as an even value. Keeps you out of trouble. Good rule to live by. So keep actually let's scoot this guy over just a little bit. So keep that coefficient as an even value. So hydrogen, we need 6. So if I put a 3 here, I would have 6. But that, my friends, is a bad number. We don't want to do that. So having that 3 there gives me the correct number of hydrogen on both sides, but it's an odd number, which means I'm going to have an odd number of oxygen. So we don't want that. Oops, sorry. So let's get rid of it. Okay? All right, so I like the 3, but let's double that. So now we have a 6, so which means I don't have 6 hydrogen, but I now have 12. Let's go on the other side and fix that one too by putting a 2 there. Little foreshadowing, yeah. So there's a 12. Now, if you need to, balance the oxygens up. So we have 2 times 2, which is 4, plus 2, it's a 6. To be honest, on a test, I wouldn't worry about the oxygens until we need to worry about the oxygens. But for some of you, you're pretty anal retentive and you like to keep that number in check. That's fine. So we've got 8 total. All right, carbon. So now we have 3 times 2, which is 6. Didn't update that, so I apologize for that. So 6 carbons. So that means that we need 6 carbons on the right side, which means that we can't put a 6 there. And so now we do need to worry about how many oxygens we have on the right side. So 6 times 2 is 12, plus 6 times 1 is 18. Okay. So now to get 18 on this side, realize that we do have 2 oxygens here times the 2. So what that means is I have 18 minus 4, which is 14. Which means that I'm going to put a 7 there to balance all this out. So, oops, sorry. Okay, so here is my balanced equation. This is my balanced equation. The question says how much oxygen or how many moles of oxygen is needed to oxidize not 2 moles, because 7 would oxidize 2 moles of this, but to oxidize just 1 mole. So if you have a 7 here, and you know you're going to divide everybody by 2, which of these would be the best answer? Very good. Okay, so 7 halves. So later on in the year, we're going to talk about thermodynamic reactions, and we will use fractions as coefficients. Notice I don't have fractions in this. All right, these are whole numbers. But when the question asks for a single mole of something, that we have to divide by however many moles we have of that substance. So in this case, we had 2 moles, so divide everybody by 2 to get your answer. So we don't need 7 moles of oxygen to oxidize or to react with 1 mole of this. We only need half of that. Okay. $39 is going to take a while. We're not going to work this one out because I want to get through the other ones. So we can come back to that one if we have time. So go to 45. I'm going to give you 15 seconds to answer this. Yeah, 15 seconds, go. What should you be looking at? Timmy, give me your answer. No, give me an answer.
Hey man, I put C.
You put C, you're wrong.
I'm calculate it out.
You don't need to calculate it out. Look at your answers.
It's A.
Look at your answers. If you see a question like this, you shouldn't even think about doing the calculation. But what kind of question is this?
Hey man.
Sig figs.
Now I got it. Now
Okay.
I got it.
Hold on, hang on. Whenever we're using equipment, okay, whenever you're using equipment, you have a graduated cylinder that only reads to 1/10 of a milliliter. Okay? It has 1/10 of a milliliter. So this determines how many decimal places we should have in our answer. Because what are we doing to this to get a volume? If we were calculating the volume. What are you doing to get a volume if you were doing this to calculate a volume? Subtracting. What's the rule with subtraction?
Take the lowest one.
Decimal places. Okay?
So
So the one with the least number of decimal places determines how many decimal places are in your answer. These all represent pretty much the same thing for this calculation. If you found yourself going 19.6 grams divided by, oh my gosh, what's this? answer here and put that there and tried to find it and didn't even look at the options before, you're burying yourself. This is where you play catch up on other questions. Yes, Sam?
I'm still confused
Okay.
why the sig figs, why it would be D.
Okay. What were you thinking? Let's go there.
Well, I was thinking C, like you said.
And a lot were. Why? I'd be willing to bet the majority of you picked C. Tell me why. There's a reason.
Because there's 3 sig figs and that's the smallest amount of sig
There's 3 sig figs. However, the decimal place trumps that. When you're adding and subtracting. In other words,
What are we adding and subtracting? That's
okay, you're finding the density. So what's the equation for density?
mass divided by
Mass divided by volume. For us to get this, we have to subtract these two values. And since we do a subtraction within this calculation, that tells us how many decimal places our answer is going to have.
So
Okay. That trumps how many decimal places. Now in front of the decimal, doesn't matter.
I have a question.
Yeah.
So do you subtract 19 grams minus 12.4?
You'd subtract this big number from that small number. And then you take that divided by all that. Yeah, Rishi.
But at the end, you're doing a division problem.
Correct. So by doing that, what we're not going to do is get a value that is going to give us more decimal places. You're absolutely right that this would be a good number because it has the right number of sig figs when you're dividing. But when you add or subtract anything, that tells us how many decimal places. So the decimal places will trump how many sig figs we have. Because this has 3 sig figs, this has how many sig figs? 5. Okay, so if we were just strictly dividing this by this, then we go with 3 sig figs as our answer. But since we're doing an addition or subtraction step within this problem, this tells us how many decimal places we'll have. Okay?
I have a question.
Yeah.
What if you, like, hypothetically, we divide first, then subtract?
You're still doing a subtraction or addition in the problem. Okay? So, as a heads up, and again, this is a learning opportunity because it is a little bit different than honors. In honors chem, I didn't do both of these together. Okay? I avoided that because that's mean. But this is reality. It can happen. Okay? All right. Everybody good on that? I know it's not a fun one. But this is definitely, you don't want to do the calculation when working that problem out. Which ones can you eliminate?
Let's see.
Just C?
And that's about it.
That's about it?
And no, actually B. Probably no.
Somebody other than Timmy.
C and D.
Kaylee, which ones can you eliminate? Or Jordan, go ahead.
No, I was telling Tim he's skinny, he can't talk.
I think.
But I
Go.
think you can eliminate D
Why?
because wait.
Have you looked at your periodic table?
Yeah, it's a lot bigger. But
Good.
It's either D or B. I can't. One of those gets wrong.
Well, look on your paper.
Well, which
Look at your paper for D or B.
they're the same thing as up there.
Good.
No. That's different.
What?
It's different.
What?
It's
They're very different.
kind
No, I mean it's the same thing as up there.
Well, I know that, but I'm asking which one. Would I eliminate B? Yes or no, guys?
No.
No, don't eliminate B.
Okay,
Can
so
I
B.
eliminate D?
Yes.
Yeah, because it's essentially it's 100 grams to 16. Out. Okay.
That's what.
Can I eliminate E?
Yes.
Why?
Because, I mean,
It's 100 to like 40, right?
yeah.
Oh, the answer's obviously A. B is obviously B. Sorry.
What I'm not telling you is the answer. What I am trying to help you with is
Wait,
being
no,
able.
it is.
It's A.
It's A, because
That's-
360
first of all-
times 3 is 48.
First of all-
52, like, wait, no, 1.62 is not. Sorry.
It would be a lot quicker if you remember chromate, which is...
No, you don't need to remember any of that. This is essentially 54 versus what? What's 3 times 16? 48. That ain't 1.6. That's a 1.
Sorry, I was just thinking. I was just trying to get them close. I had to go to the next step.
This is the mental math that we need to be doing.
This is
Okay.
rough in here.
I will condition you.
Can I come over tonight
No.
and do this?
All right, next.
Oh, no, wait. Why is it B?
Confused.
Yeah.
Why is it B?
Yes.
Because we eliminated everybody else.
But B is 54
Sam, come on, I
to
got this. You have to.
8
To 32.
2, yes.
So 54 to 32
Yeah.
is our best choice without doing any math.
Oh.
It's almost 1.5. It's a little over 1.5.
32, it's not.
2 times.
It's like over half than 54.
That's what we want.
I thought we were looking for the closest one to 54. I'm looking for the closest one.
It's our best. Thank you, Maddie.
Quality.
All right.
I was looking at that wrong.
28. This should take you about 30 seconds. Go.
This is easy.
Which one can we eliminate?
The second one?
1 and 2.
1 and 2? How about 1?
I mean B. I mean A.
Oh, hold on. When you're eliminating things like this, you can't come down here. Okay, well, I get you. A. Good. Okay. My apologies. Thank you, Jordan.
It's okay.
And D, also D.
Oh, very good. Why, Timmy?
Because there's a 1 in it.
There you go. Now we're rolling.
And also C. That's a ground. It's not C.
So it's obviously
Your choice of guessing is obviously better than just picking a letter.
Oh, he just got E.
so C, E,
CE?
One of them.
Well, let me ask you this. What does density do for us?
Moles.
It gives you the volume.
What else? What is density? Again, gives us mass and volume. Okay.
So I'll be right.
So can I find out what the molarity is? Was it molarity? Yeah, molarity. What are the units for molarity real quick? Moles over liters. Okay, so
Molar mass is in moles.
how?
Over the grams.
Because of the grams. Good. So this would give us our moles. And can we do anything with the molar mass for sucrose?
Yeah.
You kind of need to know that to know how many moles. All right. So technically what you would do is you would start with, what do we have here?
5%.
Now we're not going to figure it out because we don't know what it is.
Is it B?
We definitely need to know the density and you need to know the molar mass. Okay?
Why do we need to know this?
Because the density will tell us how much we have. Okay? Why do we not care about the density of water?
Because it's over milliliters.
Doesn't do anything for us. Yeah, it doesn't tell us anything about this solution. All right.
Wait,
Go ahead. Yes.
does the 5% sucrose by mass give you anything?
The 5% by mass is telling us that we need, A, we need to know what the molar mass of sucrose is, and B, that's telling us somewhat what the density is.
Why do we need to know density?
Okay.
Density, why?
Because 5%. So by mass, so every 5 grams of the 100 grams is due to the sucrose. That's essentially a density as well. But we don't know exactly what the density is, that's why you would need it.
Sure, the answer, you know, this
All right, question 53. The question asked, if 87 grams of K2SO4, which is potassium sulfate, and it gave the molar mass as 174 grams, is dissolved in enough water to make 250 milliliters of a solution, what are the concentrations of the potassium and the sulfate ions? Okay. Make sure, again, that when you're reading this question, you understand that you're not going to have a calculator. You're given quite a bit of information here, and hopefully some of your mental math will help you in recognizing that if I have 87 grams of something and its molar mass is 174, that is pretty darn close to 1/2 or 0.5 moles. All right, so you don't really have to do a really extensive calculation there. So you know how many moles you have. Another thing to recognize is that we don't have a whole liter of solution. So again, when we're looking at molarity, molarity is moles over liters. And so if I look at just the potassium sulfate by itself, okay? This is one of the strategies that you'll need to deal with while answering this question, is that I'm going to find out what my concentration of the K2SO4 is altogether, and then I'll be able to answer my question about the potassium ions and the sulfate ions. And my sulfate ion should be written like this, so I apologize if it doesn't look that way on the paper, and the potassium should look like that. So I have my 0.5 moles, and I want to divide it by the total volume, which in this case is 250 milliliters. Convert that to liters, that's 0.25. So without a calculator, hopefully you're recognizing that that is twice as much as that. So that means that my K2SO4 has a total molarity of 2 molar. Okay? In other words, there's 0.5 moles in the 0.25 liters. So my total molarity for this compound, for the K2SO4, is 2 molar. Now the next thing you need to do is ask yourself about what is this thing? Well, obviously it's an ionic compound because it gave us potassium ions and sulfate ions. So the next step is actually dissociate this thing. And we have 2 potassiums. And we know potassium has a +1 charge. You have your periodic table in front of you. So that means that that breaks down into 2 potassium ions. Okay? And the sulfate is a polyatomic. We don't do anything with that. We leave it as is. So here's how you have to answer this question. If this is a 2 molar solution, K2SO4, all of it is going to break down into the potassium ions and the sulfate ions. So if this is 2 molar and I have something that produces twice as many particles, then my potassium should have double or twice as much molarity. So that means that it'll have a 4 molar solution. If my K2SO4 dissociates, it produces a 1-to-1 ratio of sulfate ions, whereas the potassium was a 1-to-2, it doubled. So my sulfate ion concentration should be 2 molar. We're finished. Now, unfortunately, you can't really eliminate any dumb answers yet because you have to work out the math, and this is all mental math. And yes, you'll be expected to do this type of math in your head or write out, solve some of this on your paper. Okay? All right, let's look at the next one. All right, so this is a 1999 question. Question number 26 says, when the equation is balanced and all coefficients are reduced to their lowest whole number terms, the coefficient for oxygen is, that everybody should be able to do this. And in this case, since it's a combustion reaction with some sulfate or sulfur dioxide, we can still work this out. I would just say, you know what? Hey, do the inventory. So how many carbons? I have 10 here. Hydrogen, I have 12. Oxygen, I have a total, well, I'm going to skip the oxygen just for a second. Put the S here, because oxygen, we want to save that for last. So I have 1 sulfur. Oxygen, I have a total of 6. Do the same thing on the other side. So carbon, I'm going to keep it in the same order. 1 carbon, hydrogen, 2 hydrogen, sulfur, 1 sulfur, oxygen, looks like 2, 4, 5. Okay? Not that we care about that. Okay? Now, another thing to realize is that oxygen has an even number on the left side, which means that we need an even number on the right side. So, as a good rule of thumb, keep this coefficient as an even value. It's just going to keep you out of trouble. And if you need to, then you reduce when you're all finished. But make water with a single oxygen have an even coefficient. It's going to help you speed things up when you balance things. And save it for last. Please save it for last. All right, so let's start off with, well, may as well start with the hydrogen. And again, I apologize for putting it second, but sometimes we have to double it, which means we have to double this. So it's just smart to start with hydrogen in a combustion reaction. So we have 12 on this side. We need 12 on this side. If we put a 6 here, is that a good idea? Yes, because it's an even value and it gives me the same number of hydrogens on both sides. Okay. So if you want to keep track of your oxygen count, that's fine. We have 2, 4 plus 6, so a total of 10. Which doesn't mean anything, but we're just keeping the inventory. So since our hydrogen's good, we didn't have to do anything here. Let's go and put 10 in front of the carbon. So now I've got, my carbons are balanced. Let's get a total for our oxygen. So we now have 10 times 2 plus 2 plus 6. So it's 22, 28. Okay, I have 28. My sulfurs are already balanced. Didn't have to do anything to that. So now I have everybody balanced except for oxygen. And again, save the oxygen for last. So what I want to do is I want to make sure I have 28 oxygens on the left side, but I do have 4 of them right in here. So make sure that you take that into account. So I need 24 total oxygens added to give me a total of 28. This guy here, actually let's do that. So what number should I put there? Very good, 12. So the question wants to know, when the equation above is balanced and all the coefficients are reduced to their lowest whole number terms, the coefficient for oxygen is 12. C is your answer. Okay. And again, this is something that you should be able to do within a minute and a half. Okay. Just like the question before this, we're in 53. Okay. Hope that makes sense. Number 73. The volume of distilled water that should be, and this is huge, added. The volume of distilled water that should be added to 10 milliliters of a 6 molar HCl solution in order to prepare a 0.5 molar HCl solution is approximately what? Okay. This isn't a guesstimation one. We're looking for an actual value here. All right. So the best strategy to go at this is, if you know the volume and you know the molarity of something, let's find out something, okay? So what we want to do is, we're going from a 6 molar to a 0.5, okay? And this is me thinking. You might write this on the paper, you might not. It's your call. But it's me thinking out loud. So I'm going from a 6 molar, a very high concentration, to a very dilute concentration. So I know that I have, in the 6 molar solution, I have 6 moles for every liter. I know that over here I have 0.5 moles for every liter, okay? So what's happening is, my volume for my 6 molar is 10 milliliters. I'm going to add some amount of water, one of these values, to that to dilute the 6 molar to 0.5 molar. So the way to do that is this. Start off with your volume and molarity. We want to find out, number one, just like with the story of Little Beaker, which I know a lot of you love. Little Beaker deals with something kind of unique. And again, this is not, you don't want to go over the story of Little Beaker while you're working this problem out. But you should have the story in mind. Okay, so here we go. So this represents my stock solution. Okay. And let's say that I have 6 liters of it. Or, I'm sorry, let's not say 6 liters. Let's say that it's a 6 molar. Okay, so that's a 6 molar solution. I'm going to take 10 milliliters. This is obviously not to scale. I'm going to take 10 milliliters of my stock solution and pour it into, well, normally you pour it in, or measure it into a graduated cylinder or a pipette, one of the things. So what's cool is, when I look at my little beaker and my stock, my 6 molar, actually let's write that. My 6 molar solution is in my stock and in little beaker. These are both 6 molar. Okay, the concentration is the same. Then what I'm going to do is I'm going to take my 10 milliliters, I'm going to put it in here, and then I'm going to add some volume of water and dilute this thing out. I don't know if I can, I can, but it's still dark. It's still dark blue. We don't like that. So I'm going to pretend for a moment, let's put that back over there, that you're colorblind, and that when I add my volume, that's light blue. Okay? That's light blue. Okay? Light blue in color. And this is my dilute. So in this situation, the number of particles that I took from here and put into here are the same. The number of moles are the same in little beaker and in my dilute. So however many moles, and I don't know how many moles I have yet because I haven't done a calculation, the number of particles, the actual particles in that solution, okay, that are in here are now going in here. These number of particles are the same, except now these particles get spread out farther because I'm adding more water to it, making it more dilute. They don't get bigger or smaller, but they get more spread out. Okay, I hope that makes sense. Okay, so let's see here. Okay, so what I need to do, actually let's get rid of you, is what I need to do is I need to find out how many moles I'm going to need in my dilute solution from my 6 molar stock solution that I placed in a little beaker. All right, so here's the process. I know the volume and I know the molarity. If I multiply the volume times the molarity, what do I get? Very good, moles. And we're going to be using that same exact equation when we talk about acids and bases. So let's do that real quick. Okay, let's actually delete that. Okay. So we'll take 10 milliliters. And if you want to convert that to liters, excellent. You're moving along in the right direction. Okay? And we'll multiply that times 6 molar, which looks like this. Okay? So in your head, you're going to say to yourself, oh, okay, that right there is 0.01 liters. And if I multiply that by 6, now I have 0.06 moles. Okay? That's important to know. You have to know that. Okay? So we have a 0.06 moles. And the question says we're going to go from 6 molar to 0.5 molar. Okay? So if we know we have 0.06 moles of solution, okay, in both the dilute and little beaker, we have that same number of particles in both of these 2 containers. Not in this one, because this is 6 molar. But if we have that number of particles in both of these solutions, that number will not change regardless of how much water I have or how much water I evaporate. That number is a constant because that's not going to evaporate. So here's what you need to do. You need to write an equation and say, okay, well, I wonder, I'm going to use the variable x because I don't know how much that is going to, how much of the volume is going to give me this value here. Okay? So what I'm looking for is I'm looking for a value that when I have it here, and I take this and divide it by that, will give me 0.5. Okay? So if you need to, you can take this variable, whoops, sorry. If you need to, you can take this variable and switch it with this variable. Okay? So you can rotate those or change those. Okay? So if I take this, move it down here, and that, move it over here, put that right there, that makes the problem just a little bit easier. Okay? And if that bothers you, then say, okay, well, I don't really like that number. I'm going to write 1/2. hey, you know what fractions are. And remember that if you take a number divided by a number divided by a number, what that really means is that you're taking that number divided by 1, and we're going to take that 2, and we're actually going to move it up here. And if you do that, then it's 2 times that. Oh, interesting. And also the unit liter will, the moles go away, and the liter, technically, if I do it like this, the liter also comes up with the 2. So the moles cancel out, so 2 times that gives me a volume, which is, what is that, 1.12 liters. Okay, so let's put this, let me go back and show you that again. Okay. All right, so here's what I did. So we have our number of particles in little beaker in the dilute solution. I changed the value 0.5 to 1/2. When you take a value, the inverse of the inverse is always equal to x. So that divided by that equals that. So what I'm essentially doing is I'm getting rid of that division line, moving the 2 up, multiplying it on both sides, getting rid of that, moving that up, putting it there. The moles cancel out, so 2 times that gives me my answer. So that's the total volume. Now this is where a lot of students go wrong. That's the total volume, okay, of the solution. The question asks how much water should be added to the 10 milliliters. So you start off with 10 milliliters. You need a total volume of 0.12, which is how many milliliters? That's right. It's 120 milliliters. So if you start off with 10 and you need a total of 120, which is your answer? And I'd be willing to bet that if you didn't watch this video, you chose E rather than D. Okay? So it's not asking for the total volume, it's asking how much needs to be added. So again, when working out these types of problems, please, and I'm guilty of this as well, so I have to stop myself, and before I bubble in an answer, just take another look at the question. Look at the words that you've highlighted. Probably that's the one word that I definitely would highlight. I would spotlight that because it was even bold-faced. Sometimes they'll bold it, sometimes they won't. But slow down. Don't be in such a hurry. I know the answer. I know the answer. I'm going to get this one right. And then you write this, and you're really upset because you knew how to work this problem out, but you just didn't read the question carefully enough. So please, read the question carefully. Take your time. You have 1.5 minutes. Again, answer those questions which you know. This would probably take close to 1.5 minutes, maybe a little bit over. But there are other questions that you're going to see that it's going to be one of those type of deals. Okay? All right. All right. 2002, question 26. The question asks, approximately what mass of CuSO4, and this is a hydrate again, it's got that big black dot there, the black dot, of 5 water molecules, so this is copper sulfate pentahydrate, which you don't need to know the name of that, and it gave you the molar mass. So you don't need to worry about calculating the molar mass, okay? So there it is, there's your molar mass. It is required to prepare, oh man, they love 1/4 of a liter here. So to prepare 250 milliliters of a 0.1 molar copper 2 sulfate solution, okay? All right, here's what we know. We know we have 1/4 of a liter. We know that. We also have a 0.1 molar. Okay? And we also have a mass. So we have everything. Now it's just a matter of putting all these pieces together in the correct order and getting an answer. Okay? So here's how you do it. All right, if you know the volume and the molarity, that's a good place to start. Start with the volume. So you know you have 0.25 liters. Multiply that times the molarity. which is 0.1 moles per liter. If I stopped right there, what unit would I have? Very good. I would have moles. Okay? The next thing, the question wants us to calculate the approximate mass. So it says that there's 250 grams for every mole. Let your units tell you which way you should be going. So moles are here, they're gone, and now it's just a matter of doing some calculations on your paper. Here's a really fun trick, especially if you know your 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 3. Well, if we look at 0.25 times 0.1, that gives me a value of 0.025. Don't believe me? Work it out on your paper. Don't get your calculator out. Okay? So essentially what we have is, the way I look at it is, I have 25 times 25. What is 25 squared? Well, you probably don't have it memorized, but 25 squared is 625. Okay? So you may not have that memorized, but it's probably something you want to know just for squares. But if you see you have 625 and you have, say, 250 times this, that means that you get to move the decimal. Well, you know you have 625. Which of these answers has a format of 6, 2, and a 5? That's your answer. Okay, so once you have figured out what all these values equal, all right, I think it's pretty safe to say that that's going to be your answer. Okay? All right. So again, yes, you don't get to use a calculator. True, it's not very fun not using a calculator. I get it. But you're going to see a lot of questions like this on the multiple choice where you don't get to use a calculator. All right, the last one, 69. I think it's the last one. Yeah. Last one, 69. If 200 milliliters of a 0.6 molar magnesium chloride is added to 400 milliliters of distilled water, okay, so it's just 400 of pure water. Okay, we're diluting this thing. What is the concentration of the magnesium in the resulting solution? Now this is pretty easy. Really, it is. So the first thing that we need to do, okay, we have our stock solution. If you have your stock solution, find out how many moles you have. So it's all a matter of going back to little beaker. Okay, you have your stock. Remember that the concentration in the stock and little beaker are the same. The number of moles in little beaker and the dilute are the same. So what we need to do in this situation, let's go back, is we need to find out first how many moles we have. And then what we're going to do is we're going to add some more water to this thing and get a new molarity. And then we're going to ask ourselves another question. So we want to find out the molarity of the total solution and then answer the question. So first things first, 200 milliliters. Hopefully everybody knows that 200 milliliters is, my thing is not working there. 200 milliliters is 0.2 liters. So get in that habit of doing that mental math real quick. So I have 0.2 liters, and I'm going to multiply it times 6 moles. Okay, so again, that cancels. 0.2 times 0.6 is, very good, 0.12. And that is in moles. All right, so now that we know how many moles we have, let's find out what our concentration for our magnesium chloride is. So we're going to take this, we're going to take this value, I'll rewrite it. We're going to take our 0.12 moles, okay? And if I'm going to find the new molarity for the magnesium chloride, this number down here is my total volume. So I started with 200 milliliters, and then I'm going to add another 400 milliliters. So that means that I have a total of 400 plus 200 equals 600 milliliters. How many liters is that? Very good, that's 0.6 liters. So if I have 0.6 liters and I have 0.12 divided by 0.6, what is my concentration? Very good, it's a 0.2 molar solution, 4 moles per liter. Okay. All right, so we have our concentration for our solution. All right, again, just like with the potassium sulfate question that we had earlier, that if we have magnesium chloride, and that breaks apart, when it dissociates, it forms magnesium ions and 2 chlorine ions. All right. Now this would be a much better question if it were asking for chlorine. If it were asking for the chlorine ions, what would you guess your answer would be here? Very good, it'd be C. But since it's asking for the concentration of magnesium, let me double check that. For magnesium, then our concentration of our solution, which is the magnesium chloride, for every 1 magnesium chloride, we produce 1 magnesium. For every 1 magnesium chloride, we produce 2 chlorines. Well, we care that this is 0.2, therefore that's going to be 0.2. So really, if you're looking at the resulting solutions, this is a 0.2 molar and this is a 0.4 molar. Because again, we have twice as many particles in that volume. We have that many particles in that volume for our magnesium. Okay? All right, so again, don't freak out. I know that a lot of you are really anxious for this first test, but again, you know this stuff. You know this stuff. It's just a matter of reading the questions carefully. Please read the questions carefully. Use your time wisely. If you don't know it, skip that question. Don't put your pencil up in the air and think and think. You should be writing. You should be thinking. Think on your paper. Take little side notes. Draw pictures if you need to. Okay? Pictures are awesome. Pictures bring back great memories. So be sure to show pictures and a lot of things when working these out.